In section 4 of chapter 10, we're going to be going over what are called natural logarithms. So if you recall, back in the day when we were first discussing exponential functions, we first started dealing with like a financial system where things were compounding over certain intervals. It was a complex looking equation. But eventually we did a lesson on, hey, what happens if the number of times we compound a value turns into infinity? Basically, every single time you hit the refresh button, it is growing in value. We found that this number e popped up from Euler's number, e. E is really, really important for exponential functions. Well, seeing as how logarithms are the inverse of exponentials, and e is important for exponentials, that it would make sense to say that e must inherently also be really important for logarithms. And it is, and that's what this lesson is on. This is on what happens and how does e take a role in logarithms. So there are two special types of logarithms that all of you need to be aware of because they have some special notation to them. The first one we've already gone over. If I have a log with a base of 10, we typically do not write the 10. What we instead write is just log. If the base is not written, then we presume it to be a 10. This is our first special logarithm. The second type is if you have a log with a base of e. When you have a log with a base of e, remember, e represents for exponential growth. That represents things that happened in nature. That represents like a tree falls in the woods. It doesn't just slough off mass, it doesn't just throw away weight at the end of every single night. It's continuously decomposing at every single nanosecond. And that's where E is used to measure. It measures things that are always happening, that are happening continuously. That typically models things in nature. So the logarithmic extension of that, with a log base of E, is called the natural log. Now, unfortunately, at least for us English writing and speaking folk, the person that discovered it was someone from France. So the utilization of the language that they use is based on French. Now, forgive me for butchering it, but the way that it was told to me on how to pronounce it, it is logarithm et la naturale. LN. That represents a logarithm with a base of e. So if you ever see LN, recognize that just means you're dealing with a logarithm that has a base of e. The last little side note I want to give to this is you will see most people when they handwrite logarithms, specifically natural logarithms, they write this as capital L lowercase n. But if you see this on any kind of calculator or any kind of textbook or online resource, for some reason it baffles me, they write it as a lowercase ln. Realize they're the same thing. Most computer programs use lowercase letters. Most handwriting uses capital letters. I recommend capital letter for the L because otherwise it can look like a 1, but technically it's up to you. Here are the 7 properties of logarithms. Those 7 properties also apply to natural logarithms. So for number 1, if I have log base x of 1 equals 0, if I wanted to write 7 properties for natural logs, which you shouldn't do, but if you wanted to, that means if you are ever given a natural log of 1, that is also equal to 0. Because that's the same thing as saying e to the 0 power is equal to 1. Property number 2. If the base of the logarithm is equal to the interior of the logarithm, then it's equal to 1. That is the same thing with natural logs as saying the natural log of e. The natural log of e is just 1. And then problems 3 and onwards kind of adhere to the same rules. If I have the natural log of a to the power of b, that's the same thing as b times the natural log of a. For number 4, if I have the natural log of a times b, that is the same thing as the natural log of a plus the natural log of b. Oh, why did I make that capital? There we go. Property 5, same thing. If I have the natural log of a divided by b, this time I felt like writing it like a fraction. That is the same thing as the natural log of a minus the natural log of b. Property 6, if I have e to the power of the natural log of a, then the base of the exponential, the e, is equal to the base of the logarithm. The base of the logarithm for a natural log is also e. That just means this is equal to a. And then finally, property 7, if I have log base a of b, that is the same thing as the natural log of b divided by the natural log of a. Here are my first 2 problems. Problem number 1, I have e to the power of 2 times the natural log of 3 minus 5 times the natural log of 2. Immediately I realize I have e to the power of a natural log. That screams at me that I'm going to have to use Rule 6. However, in order for me to use Rule 6, the power, the exponent, needs to just be a single logarithm. It's not. It is a logarithm minus another logarithm. That means I'm going to have to use more properties to turn that exponent into a single logarithm. First things first, and this is very typical of logarithmic problems. The first rule we'll apply is Rule 3, because I have a 2 times a natural logarithm, so I can bring that inside as an exponent. I have a 5 times a natural logarithm, I can bring that inside as an exponent. So this will turn into e to the power of the natural log of 3 to the 2nd power is 9, minus the natural log of 2 to the 5th power is 32. Now I can utilize another rule because I'm subtracting 2 logarithms. That is property 5. Property 5 says if you're subtracting 2 logarithms, you can turn that into a single logarithm through division. So this is 9 over 32. Now I can use property 6 because the base of the exponential is an e. The base of the logarithm, which we don't write, is also an e. Therefore, according to property 6, these would cancel, and you're just left with the interior of the logarithm as our solution. Problem 2 I felt like throwing on there because I wanted to remind you all what fractional powers do. Because the first thing I'm going to do is I recognize I have a 1/2 times a natural log. That can go inside as an exponent. And I have a 1/3 times a natural log. That can go inside as an exponent. I'm not going to do that in my head. I'm going to write out what I'm doing. This is the natural log of the quantity 16x to the 4th, all to the 1/2 power, minus the natural log of the quantity of 8x to the 3rd quantity to the 1/3 quantity. I'm going to take that 1/2 and I'm going to apply it to the 16 and the x to the 4th. A 1/2 is simply a square root. It's a second root. When I square root the 16, the square root of 16 is 4, because 4 times 4 is what would give me 16. The square root of x to the 4th is saying what value times itself is equal to x to the 4th. That is x squared. Minus the natural log of. Now I'm going to take that 1/3 power and distribute that to the 8 and the x to the 3rd. A 1/3 power is a cube root. It's a third root. The cube root of 8 is saying what one number times itself 3 times is equal to 8. And that is a 2. And the cube root of x to the 3rd is x. Now I can utilize, again, I'm going to utilize property number 5 because I'm subtracting 2 logarithms. That means I can bring them together through division. This is the natural log of 4x squared over 2x. That is simplifiable because 4 divided by 2 is 2. And x squared divided by x is x. There's my answer in simplified form. The second 2 problems are now we're going to be utilizing the 7 properties of logarithms to now solve equations. So different than the last 2. The last 2 I was simplifying. These 2 I'm solving. That means I have an equal sign. That means I want to end with x equals number. Problem number 1, I have the natural log of x minus the natural log of 2 equals 5. According to property 5, if I'm subtracting two logarithms from one another, I can combine them into a single logarithm through divisions of their interior. This is the natural log of x over 2 quantity equals 5. Logarithms are not designed to solve problems where the variable you're trying to solve for is inside of the logarithm. This is like trying to cut down a tree with a hammer. You're using the wrong tool for the job. Logarithms should not be used here. Therefore, we should convert out of it. That a to the b power equals c can convert into or convert from, which is what we're going to do. Log base a of c is equal to b. This is something we went over at the very beginning of this chapter. This problem is not using logarithms in their most efficient way, so I need to convert it from a logarithm to an exponential. The base of the logarithm is an e, so this will turn into e to the 5th power equals x over 2. I need to get rid of the division of 2 by multiplying both sides by 2. And that'll give me the answer x equals 2e to the 5th. Problem number 2 is more of the same thing. There is one thing that makes it unique, but we'll go over that in a second. I have a logarithm plus a logarithm. I am adding two logarithms together. To me, that screams property 4. Property 4 deals with two logarithms being added together. I could just multiply their interiors. This is the natural log of 4x minus 11 times 2 is 8x squared minus 22. Don't forget to multiply the 11 by the 2. If you want, you can use the same conversion that I did on the first problem. It will work, but then you would have to then utilize property 6, which again will work. However, if we take a step back and look at the problem, realizing that logarithms are an operation, just like squaring or square rooting, adding, subtracting, multiplying, dividing. If I'm doing the same operation to both sides, I'm really not doing it at all. Another way of thinking about it is, if I take the natural log of a quantity and say it's equal to the natural log of a different quantity, the only way those two things can be equal is if the interiors are equal to each other. So I could rewrite this as 8x squared minus 22 is equal to 27. And these are problems that we've dealt with in the past. I need to get x by itself, so I got to get rid of the second power, the 8 and the 22. Get rid of addition and subtraction first. Then we're going to get rid of multiplication and division. So I'm going to divide both sides by 8. Put my answer over here. X squared is equal to 49 over 8. Square root both sides. Don't forget your plus or minus. That's going to give me x is equal to the plus or minus the square root of 49 is 7. The square root of 8 simplifies into the square root of 4 times the square root of 2, which then simplifies into 2 root 2. I don't like radicals in my denominator, so I'm going to multiply the top and bottom by the root 2's. And that'll give me my final answer, x equals plus or minus 7 root 2 over 2 root 2 times root 2 is 2 times root 4. 2 root 4 is the same thing as 2 times 2, which is 4. There's our final solution for problem number 2.